With this video, what I want to do is basically show you kind of an approach that I hope will help you see a lot of the similarities between different types of problems and recognize when you want to use a particular technique for solving a certain problem. So this is really going to focus on identifying and solving problems related to transient CMFRs with no reaction. And basically what I'm going to do is I'm going to go ahead and derive the full equation for all CMFRs with no reaction that are transient. And I'm going to show you 4 different situations where you might want to use this type of equation and how basically to get there. This is complementing my earlier video on transient CMFRs, but it goes about it a different way. So what I want to do is tell you first how you can identify types of problems or situations where you would need to use this kind of method. And basically what I'm talking about here is problems with transient, completely mixed flow reactors that have no reactions. So first, what is a CMFR? So this is a flow reactor. It could be a tank, a room, any sort of reactor with mixing throughout, or a lake. And basically what this needs is flow into and out of the reactor. Transient basically just means that something is changing with time. So if you ever encounter an issue where you need to see what a concentration is at a certain time, then likely what you're going to need to do is solve for a transient system. So some examples might be if you have a recent introduction of a chemical or pollutant to a system, and you want to see how that system changes with this recent introduction. Or maybe you have a recent cleanup of some type of pollutant into a system. So recent cleanup of the inflow. One example might be if if a source of pollution was eliminated, or if a treatment plant was updated. Or maybe you're looking at reactor startup. Here, I'm only going to consider systems with no reactions, so no generation or consumption terms. Basically, we're only looking at systems that are changing due to changes in inputs. And also, I would like to say that these CMFRs could contain any fluid, liquid, or gas. I'm going to be very general here. So here is my CMFR. I've just drawn it like a box. I have some sort of flow rate coming in, and I have some sort of concentration coming in. My reactor has a volume of V and a concentration of C. I'm going to go ahead and erase this in because for all of these problems, I'm going to assume that the volumetric flow rate out equals the volumetric flow rate in. So the volume of, like the main volume in the reactor isn't changing. And then I have a concentration C coming out. So it's really important to remember that these CMFRs are completely mixed. That means that our concentration C also equals our concentration coming out. And this concentration is going to change, but it's only because of some sort of dilution by maybe a decrease in Cn or an increase in Cn due to something. Again, we're not dealing with any sort of reactions here. So we're going to start with our overall mass balance equation on this reactor. So our accumulated mass equals the mass in minus the mass out plus or minus any sort of reaction. I'm going to go ahead and get rid of that reaction term because, like I've said several times, we're not doing anything with reactions. So I've got a changing concentration inside my reactor with time. I multiply that by volume to get the mass accumulated. And then I have calculated mass in and out by multiplying the flow rates by the concentrations. So when you look at this equation, you see again how very important it is to remember that the concentration within your reactor equals the concentration exiting the reactor. So our C in the accumulation term is the same as the C in the out term. If you don't remember this and you try to solve this integral, you're going to make a mistake because you're not going to realize that those terms are actually the same term. So what I'm going to do here is I am going to very painstakingly go through each of these steps so you can see exactly how this math works. So I'm going to divide both sides by V, and then I end up with this term tau, which is the residence time, equal to V over V naught. And that allows me to simplify. I can pull that 1 over tau out of my Cn minus C minus term, or Cn minus C. And then I will go ahead and I need to put all of those C terms onto the left side of the equation. So I'll go ahead and divide or take dC over Cn minus C, and then I'll move that dt over to the right side of the equation. So now in order to solve this, I need to do an integral. At this point, if you're just solving these equations, you might want to be cognizant of what terms are 0 and just make them 0. But now I'm going to take C naught to C and T naught to T. So I'm not eliminating any of those terms that I did in the previous example in the other video. What you will find whenever you're doing these kind of math problems is that in different situations, you're very likely going to use basically the same integration rules. And the one that I'm writing here is one that you're often going to apply to this type of problem, that is transient CMFRs. So it's a good one to memorize. So basically, if you look here, X is going to be C, and then A is going to be minus 1. So I'm going to go ahead and just write out the whole entire integration. So on my left side, I'll integrate it using C and then subtracting the integral, or the integrated version with C naught. And then the integral on the left side is just going to end up being T minus T naught. Now I'm going to play around and do some math. Remember, if you've got natural log of something minus natural log of something else, you can divide those two terms and put them both within the natural log. And basically you end up with this. Remember, this is complicated, but in reality, you probably would have eliminated some terms if you're working on it. I think for this example, I'm keeping everything in. This is nice for educational purposes, but in general, eliminate terms at the beginning, which will make your math much easier towards the end. You can pull out this equation if you have access to it. If you don't and you're deriving it, don't solve it this way. Make it easier if you can. But this equation will suit our purposes today. Remember, you can undo that natural log by taking the exponent. And then I'm going to go ahead and I need to isolate the C term. So this is the concentration within the reactor and also the concentration leaving the reactor. Most of the time when you're solving these problems in an engineering context, what you're actually solving for is the concentration in the reactor or leaving the reactor. And so basically, since I've got this absolute value, I'm going to have to define two cases. So one is where Cn is greater than C. So we don't really have to do anything special there. We just take away our absolute value signs. And the other situation is where Cn is less than C. So in this case, I'm going to flip those two around on the left side and solve for C. And for the purpose of this video, we're going to call these equations 1 and 2. So now I want to go through some examples. I'm going to keep these really general. And basically what I want you to do is look at these examples. I don't really give that much information, but see kind of what the big points are so that you can identify the important information in a more kind of complicated and fleshed out problem. So first, what I'm going to do is I'm going to take a starting concentration of C naught at some time T naught equals 0. And this is going to be in some sort of CMFR, like a room, tank, lake, etc. And basically I have Cn is going to equal 0. And so basically we've got this starting concentration C, or we have a starting concentration C naught, and then the fluid flowing through the system is clean, so that concentration inside of our reactor is going to decrease with time. If you've seen the other Transient CMFR video, you will recognize that this is very similar to the stinky classroom example that I gave. Okay, so because C in is 0, C in will always be less than C, the concentration inside the classroom. So in that case, what I'm going to need to do is use equation 2. So I'll write out the full version of equation 2 here, but what you've already seen is that we're going to be canceling out T naught and C in because both of those are 0. And what we end up is this equation, which is exactly what we derived in the stinky room example. If I were to graph this out, looking at concentration in and out of the reactor versus time, you would see that concentration C naught at time 0 is going to be decreasing and will approach 0 at some time. And basically, if you were trying to see if, like when the concentration reached a certain point, you would solve for T. Or if you wanted to know the concentration at time whatever, then you would solve for C. So our second example here is we've got some sort of starting concentration. C naught in our reactor is 0. And then all of a sudden we have a steady stream C in beginning at time T naught. And so maybe this is, I don't know, someone starts polluting a body of water or whatever, so, something like that. So all of a sudden you have an input. And basically you're going to see it rise steadily from, or the concentration inside the reactor rise steadily from 0. So here I am writing down equation 1. And basically I've got T naught equals 0 and C naught equals 0, so I can simplify it. And if I were to take this and graph it, basically what you would see is C naught equals 0 at T naught equals 0, so right there at the origin, and then we've got a steady increase up to some concentration. So this is going to approach Cn. So my next two examples are going to be a little more complicated, but really demonstrating the exact same thing. So for my third example, we've got a starting concentration C naught that is smaller than a new steady input Cn that starts at T naught. And so this is really similar to B, except that the starting concentration isn't 0, it's C naught. Well, it's some non-zero C naught. And so again, we're going to start with equation 1. But what we're going to find is that now we can't use any we can't cancel anything out. And if I were to graph this, what you would see is we would have some sort of steady concentration in our reactor, C naught, that's non-zero. And then at T naught, you start to get an increase. And that is going to approach, or your concentration in your reactor is going to approach Cn. And we'll throw in a little math term here. At T naught, we have a discontinuity. So the graph totally changes. And if you were working in Excel, you would have like a change in the way you're making your spreadsheet at this discontinuity. So my final example, we have some sort of starting concentration C naught, and the input stream suddenly will have the concentration of Cn is less than C naught, starting at time T naught. And so maybe you could think of like, maybe this is like some sort of lake impacted by a wastewater treatment plant, and all of a sudden that treatment plant gets an upgrade. And so Cn is coming from that plant, it's going to change. So again, this time we're going to be using our starting equation 2, but we're not going to be able to eliminate any terms. If I were to draw this, looking at the concentration inside and coming out of the reactor, I would see I have a starting concentration C naught, which is steady until time T naught, and then that's going to decrease with time. And that's going to approach Cn, and again, I'm going to see that discontinuity at T naught, where something is obviously fundamentally changing in our system. So I hope that this is helpful. I'm hoping that you see highlight some terms that you might see in different sorts of situations, and now you know what to do. Recognize that the shape of the curve depends on tau, and what you can do is you can make an Excel spreadsheet or a spreadsheet and look at the way different taus or different residence times changes the shape of that curve. So that brings me to the end of this video. Hopefully you've gained a little bit of insight into different strategies for solving transient CMFRs, and you can see a little more easily with this side-by-side comparison of how you would apply this analysis to different situations.